Okay. I'm not too early, am I? There'll still be some people filtering in, so just ignore them as they come in. It's all part of the act. Thank you so much for coming along today. Thank you so much for some of you sitting close to me so I can see you. For those of you at the back, I hope you don't have nosebleeds. I have tried sitting back up there, and I do get extreme vertigo and have these periodic nightmares about rolling forward. So if that happens and you see a sort of techie sort of roll past you, just grab them as they go past. It's all fine. We're all friends here. Earlier on, you would have seen the podium here collapse. It was really exciting. I'm not going to touch it or go too close to it, but if that does happen as well, just assume it's part of the performance, and there's nothing important to see here. We are actually here to talk about security, so thank you very much for coming along. We're going to be talking, I've done a talk a couple of years ago at NDC, also this is my 5th year here, talking about microservice security, and this is an ever-changing field, and so this is a brand new talk, really looking at some of the more recent evidence out there, new technology, new techniques, and sort of helping. I'm going to try and help you focus on what I think are the things that are most important to worry about in the context of microservice security. I've also written a book. Some of you may have read the book. If you haven't read the book, you should definitely buy it. Copies for your friends, families. It's always good when it's cold. I mean, it gets cold here in the Nordic areas. It burns really well. So that's fine too. I'm actually working on a 2nd edition, and a lot of the content you'll see today are working its way into the 2nd edition. I also run my own training and consultancy firm. If you want to know more about the work that I do come and find me afterwards or find details at my website. The field of security gets a lot more attention than it used to do. We used to operate in a world where security was sort of somebody else's concern, but now we're surrounded by press releases outlining the problems associated with security breaches. It makes the news. We now have regulations that come into force that change the way we think about implementing our systems that are being driven around new concerns around security and privacy. I can kind of track this in a way to the sort of shifting perceptions around data that occurred post-Snowden, that also occurred at the same time that we're starting to consolidate more data together. Consolidating more data together to give our customers value is also, of course, creating a fantastic target for other people to take advantage of. And so now when breaches do happen, they happen en masse and with some pretty sensitive data. We have things like the Equifax data breach in the US, which we'll come back to a bit later on. We've got Meltdown and Spectre. Now it's even our chips that need to be patched. We used to think that some things were safe, and now we're having to worry about applying firmware to protect ourselves against fundamental problems in our underlying chips, which is a bit of a scary moment when you're running on somebody else's computer and you realize just how much you trust them to do. And of course, GDPR is changing drastically how we think about where data lives. In many ways, this is a boon for people that have not touched their legacy systems for 30 years, because now they get to do it right, rather than all those people that have spent the last 10 years re-architecting their legacy systems, only to find they've got to change how they think about data and the storage of data due to GDPR, which I think is very sensible legislation, by the way, on the whole, in terms of the things it forces upon us in terms of how we think about looking after our customers' data, doing things like mandatory data reporting of breaches, and really thinking seriously about how we treat something that is deeply private and personal to our customers. But we have this issue that we've got all-encompassing when it comes to application delivery over time. We used to just think about the development of our software. We now think of it much more as a holistic process. The process from designing our software to actually developing it, writing the code. We then test our systems, and we now think about writing those tests ourselves, bringing that testing process into our delivery teams, and then finally shipping our software, hopefully to the universal delight of the audience. And lots of money will rain down upon us. And if it doesn't, that's okay, because we'll go back and we'll tweak the application again and we'll do it all again. And we're into this groove of incremental delivery and iterative delivery, putting more and more processes into that fold and rolling it around. It's great, it's fantastic. And you look back 20 years ago, how we thought about software development, where it's a much more siloed, waterfall type activity. It's rather, we're trying to break these barriers down and bring everyone working together. And of course, there is something missing here. We sort of just, security's on the one side. We don't really worry too much about that. It's sort of like do you want fries with this mentality? You go into a nice restaurant and you order a nice, big, fat, juicy steak or a lovely nut roast, if that's the sort of thing you're onto, and the server will say, do you want some fries with that? And you say, I'll sprinkle some fries along the side. And we have that same approach to security to an extent. We sort of create our lovely system, and someone goes, should we make sure it's Should we make sure we've looked after our customers? Hey, oh yeah, go and have a look at it, that's fine. But I've got more important things to worry about, right? And the reality is when it comes to something like security, as it was with testing and quality, as it was with things like thinking about the application design, the usability, these aren't things that can be applied in a siloed mentality. We sort of have to find ways to break those walls down. Now, I'm not suggesting that you don't need experts. Sometimes you do need experts, people with specialist skills, and sometimes matching outfits to come in and help you. There are a role for experts, but I think in the past what we've done is we've abdicated all responsibility to experts, which I think is unfortunate. We don't do that with testing anymore. We accept that having separate people that do all of the testing for us and having us abdicate responsibility as developers to those individuals is suboptimal. And the same thing, I think, applies when it comes to the field of security and application development. We don't need to become experts. We just need just enough security to be a little less dangerous, to build a little bit of this thinking into our working practices and the software that we create. We still need experts, but we shouldn't rely on the experts for absolutely everything. We can be a bit more generalist about these things as well. We're here to look at this in the context of microservice architecture, and this is always a sort of picture I draw of microservices. You know, I always like drawing hexagons. It's partly as a really subtle message to buy my book because there's hexagons on the cover of the book. It's also partly because it's a nice shape, and there's a lot to be said for the world for having nice shape in architecture diagrams, especially when you spend all of your time looking at boxes and arrows. You might as well at least have a nicer shaped box. When I talk about microservices, what I'm focusing on much more here are the outcomes. I don't tend to talk too much about the technology aspects of that. You know, for me, I'm looking for the outcomes of things that a microservice architecture lets me do for my customer, for my user. And a lot of those drivers come from this idea of these independently deployable services. That's what we think about a microservice being. The ability to make a change to a service and deploy that service independently of deploying anything else. And that's the sort of way, the thing that drives many of the benefits from a microservice architecture. So separate, independent processes. When it comes to security, they open up some really interesting opportunities to us. With a monolithic system, we sort of have all of our processing and all of our data in one place. And that causes some potential issues. Here's all of my data is in one location. A single exploit might potentially gain access for an attacker to all of the data. It's sitting there, all in one place. That also means that I almost have to protect my least important data in the same way that I protect my most important data, certainly when it's at rest, because it's just all there in this big giant database. It's all there over these networks that are flowing in and out. It becomes very hard to focus your time, energy, and attention. With a microservice architecture, we talk about microservices owning their own data. And so we're often talking about how we break apart these large monolithic schemas in order to create these independently deployable services. That opens up some nice possibilities when it comes to protecting ourselves and defending our applications. We have the single egg problem now, right? I have one application, one service with its data which I can protect more strongly if it contains, for example, personally identifiable information. Those other parts of my system that process less critical data or don't store personally identifiable information may therefore require less oversight, might not fall under the same regulatory frameworks that you operate in if you're in banking, finance, healthcare, or even some things under the GDPR. This can actually simplify your process in terms of saying, yes, we are compliant, but also make it easier to focus your time and energy on the places where it needs to when it comes to worrying about the security of your systems. All of these things are, and there's lots of content out there around the GDPR. I'm not going to touch on it very deeply, but do go out there and have a look and see. I'm sure all of you understand the implications of this. It's been quite interesting how many companies do not. Lots of companies are going around asking you to say again that you want to opt into the mailing lists, for example, and claiming that's under GDPR, which is a complete and utter misunderstanding of what GDPR actually says, which has been hilarious to me, that this has been the biggest thing that people have focused on. So this idea with microservice architecture that we get to not only focus our time and energy, but also on the places where it most needs it, but also we get the ability to define multiple points of protection for our system. One of the sort of core tenets of defending systems is about defense in depth. You know, if you've got a castle, you don't just have one big wall. You have a big wall and a moat, and then you have another big wall around the moat, and then you have a big tower that's got a big thick door on it as well, and you're always worried about, okay, what happens if someone breaches that defense? Is there another defense behind that? With a microservice architecture, I've got multiple network perimeters at which I can defend and protect my application. I also have the ability to have a mix of technology that I'm using. An exploit that might work against one technology stack won't necessarily work against another technology stack. And so on the face of it, this seems fantastic, right? What I've told you so far is that microservice architectures, from a security point of view, are obviously better, and you should definitely do it. That's not what I'm saying. What I'm saying is you should definitely buy my book. But I'm also saying that there are opportunities here for you, right, to take advantage of this when it comes to creating applications that you want to be secure. I actually think teams which are smart and savvy around security concerns could use a microservice architecture to create a significantly more secure operating environment for their customers. The problem is that out of the box, the story is worse. Because ultimately, all this information that used to flow within a single process is now flowing over networks. And those networks are things that can be sniffed, that can be manipulated. A malicious party could not only intercept that data, it could even start masquerading as services in your own system. And given that the vast majority of the customers I speak to still run their data in microservice architectures over completely in the open HTTP connections, this is an obvious concern. You also have multiple services at which could be a weak spot. If I've patched 3 of these services, but not the 4th, I've potentially got a weak spot in my infrastructure. And so there is this double-edged sword nature when it comes to microservices and security. We have this problem. They give and they take away. We're going to start, though, with some basic stuff. And I'm going to ask a bit of a question. It's going to be hard because I can't quite see everybody because of the lights. But hands up who here thinks they're good at assessing security risks. So this is good. This is, you're honest. I've got a few hesitant hands. Yeah, I think I'm pretty good. My experience is that developers in general, developers like myself in general, are actually quite bad at assessing security risks. And I think you seem to agree with me. And I think it's primarily because we often fixate on the wrong things. And it's always good to actually get some outside validation that we're terrible at something. There's a really nice report from Verizon put out a report every year called the Data Breach Report. And this is from the 2017 edition. And this is mostly looking at the Verizon customers. So that's mostly North America. So it may not be generally applicable, but it's still a fairly large body of evidence from which to draw some conclusions, at least. And they looked into the mechanisms used by attackers to gain access to data. And they found that by far the single most popular mechanism used by malicious attackers to gain access to data, to gain access to that critical information that we're worried about losing, is very simply bad passwords. So that's it. So 81% of all breaches involve the use of an easily guessable or easily stolen or easily cracked password. So this is not good, but it's also great, because actually this is an easy thing to fix, right? There is loads of evidence and information out there about how to do passwords well. Whether or not you choose to follow that information is entirely up to you. Troy did a really nice blog post summarizing a whole bunch of information about good password hygiene. This is from earlier this year. So this is summarizing information from NIST in North America and the UK's Cyber Security Centre. And these are like governmental bodies. And we tend to view these governmental bodies as coming out with quite stodgy information. Information that's not really applicable in our real world, but actually turns out the advice coming out from NIST and the Cyber Security Centre is actually really sensible advice. And it's basic stuff, like, maybe allowing people to have a long password is a good idea. How many of you have gone to enter a password for a new sign-up to find that you're limited to, say, 20 characters or something like that? It's like, yeah, lots, right? Because as we all know, that 21st and 22nd character costs them a lot more money to store. Disk space is really expensive, right? And that just seems like a crazy limitation to me, because that's encouraging us to have shorter passwords, which is clearly insane. We also have issues, of course, with people requiring very complex password schemes, which require us to have come up with elaborate mechanisms to remember them, which normally ends up with people coming up with one scheme that fits, that they'll then just enumerate when they need to change their passwords. And it becomes utterly bewildering sometimes, these rules, getting all these arbitrary things that we've got to guess. And most of this is purely about trying to create entropy in the passwords. And guess what? One great way to help improve entropy on the password is allowing longer passwords. So yeah, maybe think about that. There are other problems, of course, with how we tend to think about passwords and very easy things to fix. How many of you here use a password manager for your personal life? Yeah, virtually everybody. Now, how many of you use a password manager for passwords you manage in your day job? So less than half of those people. So of the people that use password managers at home, less than half of you also use it at your work. That seems potty to me. And the fact that all of you don't have your hands up for password managers is also the concern. Get one. Go get one password. It's great. But not enough people actually use them as well for passwords in their day jobs. What does that lead to? Again, passwords being written down, passwords being very easy to remember, which means you only have a small number of them, which means you use the same passwords for multiple different services. There's another kind of very interesting piece of advice that came out of this, which is do not mandate password changes. You've seen the dialogue, oh, it's every 3 months you've got to change your password. You've got to change your password again. Oh, you've got to change your password again. Now, the concern here is that if someone gets hold of your old password, they can't use it if it's been changed. That's what this is defending against, fundamentally, is that if that password gets leaked, that they can use it. But if it's been expired, they can't use it. But firstly, if you're using a password manager, the chances of it being breached are quite low. And secondly, what does this do when you always prompt, create a new password, create a new password, create a new password? Give me your current password, here's the key thing, and now your new password. We are training legions and legions of people for phishing attacks, aren't we? We're getting people to recognize that when the dialogue pops up asking me for my current password, I should type it in, otherwise I can't get my job done. And so their encouragement here is to stop doing that. And in fact, to only start asking people to change their password when we know that those passwords have been breached, or we have a reasonable expectation that those passwords have been breached. And finding out if passwords have been breached is a lot easier now than it used to be. Finding out if one of your customers has used the same password combination somewhere else is much easier. Now we have services like Have I Been Pwned that can tell us whether or not the hashes of passwords have been used in different breaches. In fact, 1Password now integrates this feature into the latest clients for Windows and Mac. It will tell you, oh, by the way, this password, not only was your email address in a certain data breach, but also this password was in that breach and you better change it. So there's not really an excuse for especially inside organizations that should be mandating the use of password managers, not to be doing this in a smarter way. There's other great basics out there. There's a really nice piece from Justin Smith from a couple of years ago called The 3 R's. So Justin's over at Pivotal. And he was looking at some of the common defense mechanisms and actually 3 really good pieces of advice to defend yourself against one of the worst forms of attack you can have. And that's a form of attack called the advanced persistent threat. So an advanced persistent threat is a really nasty form of attack. And this isn't just some arbitrary botnet that's hacking into your site and trying to use some WordPress exploit. This is somebody that gains access to your system, that sits on your system for a prolonged period of time, hoovering up information. And these APTs tend to be behind some of the more serious breaches that we see. I talked a couple of years ago about the Target data breach, where a form of APT was basically a malware that was installed onto the electronic point of sale systems in the Target stores across North America and siphoned off credit cards over a period of many days before those were stolen. I think something like 40% of all US households were impacted by that particular breach. A more recent example of an advanced persistent threat that you may or may not view in a good light, depending on your political leanings, was a Dutch cybersecurity group that managed to gain access to the Russian hackers that were behind the Republican DNC hack. And this Dutch agency were actually able to get into the Russians' systems, watch what they were doing. They even gained access to the CCTV cameras outside the offices where these hackers were based and took photographs of all the hackers as they were walking into and out of the room. So they've now got information about all the people behind the hacks of the DNC in the US. So, you could view this in a good or a bad way. But when you have an advanced persistent threat, somebody that's on your network for a prolonged period of time, they can hoover up quite a lot of information. The 3 R's that Justin gives us are very simple. The first is rotate, and this is about short-lived credentials. Now, this seems a bit contrary to the information I just gave you. This is talking about things like security passwords and username passwords for databases. The second R is repair. Patch your stuff. Like, seriously patch your stuff. Patch your stuff. This actually gets a lot more complicated in a microservice environment. We'll talk about why in a moment. And finally, repave. When you're worried that something bad may have gone into your system, don't just try and fix it. Burn the whole thing down and start again. It's the best way to burn out an advanced persistent threat. So let's talk about short-lived credentials. How many people here have heard of code spaces? Yeah. Didn't think so. There's a reason you haven't heard of code spaces, and that's because they do not exist anymore. So code spaces were a company which, ironically enough, provided secure source code hosting. And what happened was their root Amazon credentials, this is the credentials for the core account, for their Amazon account, were accessed by a malicious party. And they never quite found out if this was a disgruntled ex-employee or if they'd just been left out in the open. This attacker used these API credentials to wipe out all of the resources in this account. So that shut down all of their machines and killed the running system. And that's okay, of course, because they've got backups, haven't they? Yes, they do have backups. The backups were in the same account, so all those backups got wiped out. But that's okay, because they've got source code, right? So they can rebuild the system. Yeah, you can see where this is going. The source code was also in the same account. And so in the space of 5 minutes, this company went from existing and having customers to not existing at all. Now, there's 2 lessons here. One, don't use one cloud account for all of your things, right? That's nuts. You want to limit what access you have via these accounts. The second thing is, don't lose those passwords and actually have them expiring quickly. Most people I know that make use of cloud services like AWS now move towards a system where they get time-limited credentials, where you gain access and you generate an API key pair that might be valid for only 45 minutes. 45 minutes, that's how short we're talking in terms of fast rotation of credentials for these sorts of systems. There are systems and tools out there that will help you pick up leaving these credentials lying around, by the way. I quite like GitRob that will look at Git repositories, and it will look for things that could be API keys for different cloud services. And so we were using this internally inside a company I was at a couple of years ago, and that worked quite well, because people sometimes accidentally check in their security credentials. And things like GitRob can pick it up. GitHub themselves and Amazon, certainly, I'm sure Microsoft is doing the same thing, will sometimes are doing these sweeps themselves and will email customers to say, by the way, it looks like you checked in your API keys. Maybe you should do something about it. Now, with a microservice architecture, having credentials for things like databases and accessing cloud resources could be quite painful, because it's not like you've got one process that you're configuring. You've got multiple different processes that all might need those credentials being changed. And that's going to experience a high degree of pain if the process around revoking credentials is fully manual. The secret here is, if you want to be able to get really good at revoking credentials and also allow you to have extremely short time-limited credentials, you need to be able to automate this stuff. And if you can automate it, then you can do it for microservices just as well as you can for a single monolithic process. In the situation here, it's like I've got things like shared secrets. So these could be things like API keys, and those are things that need to be rolled out everywhere. I might also have things like database passwords as well. If you think about it, I'm accessing my local database. I've got to have the credentials for that system. So I'm going to put in a text file, probably something like this. I'm going to say my username is admin. This is my password. This is how I'm going to access my database. And isn't that great? Now, of course, if someone gains access to that information, and if it's in a text file, that increases the chances or makes it easier for an attacker to get hold of that text. If they get hold of that username and password, they can access my database directly. So this is not good. Right? One of the solutions that you'll see for this is using something like a secret store. All of the cloud providers, well, certainly Microsoft have this in Azure. You've got a secure secret store. With AWS, you have the parameter store. There's a system I really like for handling secrets, though, and that's called Vault. And Vault is a system that you can install wherever you want. It actually is much more sophisticated than the tools that you get with the cloud providers. I would certainly say if you're with Azure or if you're with AWS and you want some sort of basic secret storage, absolutely use the tools that come with the system. But Vault has some really interesting capabilities. So I would say, if you're really interested in getting deep into this space and doing some really funky things with it, this is a good place to look at. Now, the way Vault works is very straightforward. I've got my application, and I need to get some information out. So I've got some encrypted value. So I've been given my username or my password. It's some encrypted value. And so I'm going to go to the Vault first off, and I'm going to say, well, look, Vault, can I please gain access to my information? And the very first thing I've got to do is authorize myself with Vault to say, hello, I really am who I say I am. And then that gains me access to the physical back end. And so Vault is what's going to be transparently decrypting or encrypting this information on my behalf. And the physical back end can be all kinds of systems. Like you can stick these things in etcd or console or other types of data storage. Vault is almost just like a bit of software that sits between you and where the data is stored. Now, the kind of interesting thing with Vault is imagine Vault is like a big box. It's a very secure box. And in that box, you've got all of your keys. So that's really important. And of course, you need to lock those keys up so they're safe, right? So you put all your important keys in the box, and then you close the box, and you lock the box. OK, great. And so I've locked the box with the key. OK, so where do I put that key? I could put that key in another box, and I could lock that box, but now I've got another key. And the concern is always, like, well, at some point, there's a key that if someone gets hold of it, they gain access to the crown jewels. Vault makes use of a system, a kind of a really interesting system to solve this problem. It's actually an algorithm called Chimère's sharding. And the way it works is to kind of unseal the vault. So when you launch the vault process, you sort of have to open it so it can be serving up keys to the rest of the world. You have to have a number of keys to unseal it. So in this particular example, we've got 6 keys that exist in the system that could unseal the vault. But we might configure it so that we need at least 3 of them to unseal that. And normally the way you would run this is the people that run or manage Vault in your organization. Each person would maybe have one of the keys, and you need to get hold of 2 or 3 of them to unseal that vault. That means if one of those keys gets stolen, it doesn't matter because they need more keys than that. It's basically like those old 70s films where they shut down nuclear reactors and everyone has to put the key in at the same time and turn it at the same time. So this is a bit of an operational pain that you get, but it's something you only have to do when you're bringing a vault node up. And normally you run a sort of a series of these to give yourself resiliency. So that's kind of an interesting model. So once you have Vault up and running, you can do all kinds of interesting things with it. It's not just a store for how do I store my username and password in an encrypted mechanism. It can even generate you time-limited credentials on your behalf. For example, if I'm working with either something like AWS or I'm working with Postgres, I can actually go to Vault and say, OK, can you give me my own username and password to access Postgres? And I can use that as part of my application. And that will be time limited. And so Vault has all these different configurations where it can generate those things on your behalf. It will either work with the underlying capabilities of the system, so AWS and Azure support this stuff out of the box, or it will implement that on your behalf for different databases. And so now I'm getting that nice property of time-limited credentials out of the box with Vault. And as long as my application can talk to Vault, I'm away. And one other nice thing Vault does is there's a tool called console template that does a very, very simple thing. It basically will take data from console or Vault and put it in a text file, which seems really dull until you think of all of those systems out there that are configured via text files that you don't want to have to reconfigure to talk to some fancy new Vault system. And so using console template, you could have your configuration like this in a text file, and console template will just automatically update it with values from Vault. When those credentials change, it will update the values in a text file. So all your application needs to be able to do is reread a text file, which is a pretty easy thing to do. So, OK, using a system like this, you can actually implement time-limited credentials quite easily en masse in a large-scale microservice system. I'm hoping we'll see more capabilities like this rolled out for platforms like Azure and the Google and AWS key management solutions. OK, back to other classic forms of security defects that we have to worry about, or things that cause data breaches. So another report for you. This is from a Forbes BMC report back in 2016. And they found that 44% of all security breaches occurred after basically vulnerabilities had been identified but had not actually been dealt with. So in other words, someone had said, oh, look, you've left the back door open. And then someone's gone, yes, the back door is open. They hadn't closed the back door. And then the burglars went in by the back door and stole all your stuff. Now, after that, you're going to feel a little bit silly, but it turns out it happens a lot. So we find vulnerabilities, we don't deal with them, and we get attacked through those self-same vulnerabilities. Some of the times, of course, this is just that a patch exists for something and that you haven't applied it. And often the problem is that you don't even know that a patch existed and that needed to be applied. So coming back to Equifax, some of you, how many people here have heard about what happened with Equifax? There's quite a few of you. It was mostly affected people in North America again, which seems to be the home of large-scale data breaches. This is not good because Equifax, as a credit scoring agency, had a lot of information about Americans. Again, another great case study in how not to handle a security breach. But we're going to look at one specific aspect of this. So early on, they came out and explained how this breach happened. I say early on, it was still much later than they should have. But anyway, they came out and explained that the problem was due to a vulnerability in a web framework called Struts, which is a web framework for working in Java. And a lot of people were quite sniffy about this because Struts is quite an old framework. It's sort of first-generation web framework for Java in a way, but it's still being actively supported and maintained. So although you might not like its programming style, it's still an actively maintained piece of software. So they identified that this breach had, that this attacker had used this particular exploit that has this nice long CVE identifier here, and so that's the identifier over there. And so these CVEs are quite useful because you can read all kinds of information about what caused them and what the exploit is and how it might be used. And you also get like a sense of how bad these things are as well. So if you take a look at this critical vulnerability, we get some useful information. So one of the things that you get is this CVSS score. This is a severity score of how bad this vulnerability is. And you can see there that that's 10. That's 10. That's a score of 10. This isn't out of 100. And this isn't like 10 is the good one either. 10 is the bad one. 10 is the worst you can possibly get. So this is the worst exploit you can possibly get. Now, this particular vulnerability was reported in March 2017. What this normally means is that a security researcher has found the vulnerability and communicated with the developers about what was happening, and then they coordinated the releases of patches to fix that at the same time as they reported the defect. So basically, you already had the patches available at the same time the vulnerability was announced. And this is quite common practice, because if you announce the vulnerability, but without there being a patch out there, what you're doing is giving information to attackers to use that vulnerability. So this is probably a sensible thing to do. So this is March, so keep that date in the back of your mind. 7th of March, these patches are available. So what we know with Equifax is that between mid-May and July, this data was stolen. We're not quite sure when, but between those windows. Equifax spotted it on July the 29th. That's a bit too long, so they're a bit vague about when this happened. They reported it to the public on September the 7th. That is not good, right? Taking a good, month to get back to people and say, oh yeah, we've lost all your data. So by the time they found the defects, they found the breach had occurred, we know that they probably had between a 2 to a 4 month window to have applied that patch. They had a 2 month window minimum in which they could have applied that patch and completely stopped this attacker. So it's a question for all of you. This is a 2 to 4 month window. How many of you out there are sure that every single one of your systems is patched every 2 to 4 months? Put your hands up if you're sure. Right. So, now we know patch hygiene isn't great. This is other data from the Verizon data breach report, and it shows that different sectors are less good or less bad at actually applying vulnerabilities when they occur. We see up here like the information, the IT sector and the manufacturing actually in healthcare is pretty good. Finance is awful, actually, which is a bit concerning. So what we're seeing here is how long it takes to fix a vulnerability once a defect has been found. You see, finance is pretty awful, about 25%. I think you could probably argue that Equifax fall into that bucket. There's a long tail. A lot of things get fixed very, very quickly, and there's a long tail. Now, sometimes these vulnerabilities aren't fixed because there may not be fixes. It may not be a clean patch. But we're getting better. Actually, what Verizon said is this is actually getting better year on year. I think, though, the problem is it's not getting better fast enough, especially when we start thinking about our microservice architectures. Those of us running microservice architectures are often running in a Russian doll-like situation. We're not running on a piece of physical hardware. Oh, no, it's much more complicated than that, because we've got the underlying hardware, and that hardware is running an operating system. That operating system, of course, has a hypervisor running on top of that. On top of the hypervisor, I've got a virtual machine operating system. On top of that, I've got Docker, probably, because you have to Docker. You've got to Docker. Docker, so I've got Dockers, and on my Dockers, I've got my container operating system, which, in the case of Windows Nano Container, is like, I think it's about 200 megs, right? Which is definition of nano we can talk about later. It's still getting smaller, which is good, but there's still a full operating system there on the Docker container. And sitting on top of that, I've got your application, okay? So this is the sort of stack diagram you might expect just for a Dockerized application. And now you've got to think about every single one of those layers. Every single one of those layers requires patches, including your underlying hardware. Remember Spectre and Meltdown that I mentioned earlier? So, for those of you who might have a similar deployment topology to this, I guess the question I'm going to ask you again is, how many of you are sure you're running and patching your software every 2 to 4 months? And all of those levels. John, you can put your hand up. I know you are. Right, if you work at Microsoft, you probably put your hand up. Right, that's fine. So it looks like none of you have got your hands up. And this is the thing, right, because we often forget all the things underneath us that actually do require attention. We also forget the things above us that require attention. So what are the things that we can do about this? When we think about these sort of more complex stack diagrams that we have, firstly, if you're offloading this onto a cloud vendor, you're relying on them to do this stuff for you. So if you're just using, say, cloud infrastructure as a service, you're offloading a bunch of concerns to Microsoft or Amazon or Google to look after your virtualized infrastructure. And if you look at Spectre and Meltdown, all of those providers patched all of those systems, I think, within 7 days of those patches being available. And we saw that because all of us saw a degradation in performance of between 10 and 30% overnight, which is quite annoying. If you start using higher order abstracted platforms, you start looking at, say, platform as a service, you're sort of having more of your system handled for you. If you're using a managed Kubernetes environment, for example, you're only having to worry about your container operating system and your application sitting on top. And so then you're focusing your attention on less and less and less of the stack. This is even better if you're using a function as a service platform when it's just your code and, importantly, your code dependencies. So depending on which level of abstraction you are, you're focusing more of your time and energy. We've got tools out there like Claire to do vulnerability scanning of Docker containers, so Claire and Aqua, which I really like, which sort of does an even better job of this, that can help us identify vulnerabilities across our system that can see, okay, well, you've got unpatched operating systems running there. And this is another issue with the microservice architectures. We often create a service that does exactly what it needs to do, and it sits there running for 6 months because no one needs to touch it. And a Docker container that hasn't been touched in 6 months is 6 months worth of unpatched vulnerabilities sitting there on that machine that needs to be addressed. What I find increasingly is the great last unknown is back where we were with Equifax, is actually all those third-party dependencies that you have in your system. All of those third-party libraries you use. Are you updating those? Are you checking to see if new versions of your dependencies are available? Most people don't. Now, I really love Snyk. Snyk's a really useful tool. What it does is it just looks at your source code, it looks at your Git repos, and it looks at the dependencies that you have onto other third-party libraries. They maintain their own CVE database for all different vulnerabilities from common third-party programming libraries. That's actually their biggest resources in a way. They will automatically identify that a critical vulnerability occurs in one of your libraries. They'll then send you a message saying, oh, by the way, this has got a critical vulnerability in it, you really should upgrade it. They'll even go further and send you a pull request where they update that value in the dependency files for you, and you click a button and it updates it. And it's cheap, like really cheap. This stuff is it's like $20 or something a month for a lot of teams. And this is fantastic, right? This is taking all this concern away from us. We can use tools to get better at this. The key thing, the first step, is acknowledging you have a problem. And the next step is parting with like $20 a month to fix it, which seems like a pretty good deal. Obviously, as well, when it comes to doing some threats, so understanding the threats and the risks we have, part of the problem here is we often fixate on the wrong things, as I said. And so being able to step back and looking at these things holistically and really understanding what your problems are is a good first step. So I do urge those of you who are in environments, especially that might have some sort of specific concerns around handling of PII, you might be in a heavily regulated industry, is to do some proper threat modeling. And there's a whole bunch of useful information over at Microsoft's Secure Developer Lifecycle website, but you can also read up on things like attack trees and stuff like that, which I cover in my book to an extent. I've also just done a 3-hour-long tutorial on microservice security, which I'll send out via Twitter later. So let's talk about the last sort of piece around this. I mean, a lot of people, time when we talk about microservice security, people want me to talk about transport security first. And the reality is that, yes, that can be important, but there's much more fundamental things, and that's why we talked about these other things first. I'm not going to talk to you about transport security until I've made sure you're dealing with passwords properly and you're patching your systems properly, because otherwise it's like building a glorious, massive front, big, thick wall and putting a big moat around your systems and leaving the back door open, right? So now we've closed the back door, we can start thinking about those other things that come up. And of course, we have to think about transport security, which is also obviously the cool and exciting stuff that's out there. And this is where people get quite excited. People start talking to me about different encryption mechanisms and API security and the like. But let's take a look at example architecture and examine what some of our options are. So we've got, I always like using a cutting-edge company as an example. And so I have my fake company, which is selling CDs online. I've been using it since 2011. It hasn't dated at all, because everyone's still definitely buying CDs. So here we've got our nice services architecture sitting inside our perimeter. Like we've got a catalog which tells us how much things cost. We've got a streaming back end because we've read that thing about how you scale Agile at Spotify, and we think we can now be Spotify as well. So that's working out really well for us. And we've got some customers out there. We've got like mobile and web clients out there. And we've got some downstream companies and partners that we talk to. And so then we start thinking about all this information that's flowing to us from the public internet, that's flowing downstream to other resources. And we've got to think about, well, what happens now? This information that used to be much more protected is now much more in the open. What do we do about these things? When it comes down to transport security, there's kind of really sort of 4 key concerns you've got to think about. The first is the data being observed? And am I worried about that? The second is that data being manipulated? So rather than paying Sam £100, you pay Sam £200, which I personally think is a good deal. The third one is restricting access to the endpoints. So can I stop a malicious party or an unauthorized party from directly accessing services and extracting the information they want? And finally, can I stop someone impersonating my service endpoints? This is a pretty sophisticated form of attack, by the way, but it's a really nasty one. So yeah, these are sort of core concerns. We'll start with the basics. We've of course got things like HTTPS anywhere, by which we mean, HTTP plus TLS. So HTTP plus TLS is going to give us server guarantees. We know the server we're talking to is the server we're talking to. It guarantees to us that the payload itself isn't being manipulated, so it stops man-in-the-middle attacks and those sorts of things. It doesn't necessarily give us anything about clients. We don't necessarily know who the clients are in this world. And certificate management has historically been painful. Really not a big deal anymore, certificate management, and if that's used as an excuse, then you're not really trying hard enough. I mean, if you're looking, we've got things like Let's Encrypt, which people obviously fixate on because it's free, which was never the deal, right? That was never the problem with certificate management. It wasn't the $25 you paid to Thwaite that was the pain. It was the fact that it was a manual process. These things are now fully automated. You've got, AWS Certificate Manager, you've got Azure Certificate Manager. All of these things will make this like a couple of clicks to set this stuff up. There is no excuse for not running HTTPS inside your perimeter either. And don't trot out the old, it will slow my systems down by 20%, because that was based on one benchmark about 20 years ago. So come at me with some new data, please. So in terms of how this stacks up, we're thinking about our core concerns. Well, it helps us in observation of data. It helps us with manipulation of data. Doesn't do much at the moment about restricting access to endpoints. But also, if you're properly signing certificates and properly checking certificates, don't turn off certificate checking. That's always fun, isn't it? Someone just self-signs a certificate which is completely invalid, and you turn off validation of that. That's kind of bypassing all of this. But it stops you impersonating endpoints. So maybe a good default choice for inside your perimeter, and obviously it should be a default choice for anything on the public internet. I shouldn't have to explain why the public side of this is a no-brainer. We can improve this, of course, by using something like mutual TLS, where we actually have the client also engage in that full TLS handshake by using things like client-side certificates. So now not only do I have a certificate for the server, I also have one for the client. This now gives me both client and server guarantees. This is much, much better. Historically, again, this stuff is really painful. If you're running on-premise, this is painful, I'm not going to lie to you. Even if you can issue those certificates, installing them and revoking them automatically is a giant pain in the bum. But again, if you're on Azure, this is easy. You can install these things in the API gateway and have that actually terminate the client handshaking. This is all there's a whole lovely little step-by-step. Look, there's like 10 steps. 10 steps. If you're on Azure, there's no excuse. So again, if this is why your system gets cracked at some point later on, it's your own fault. Obviously, AWS has exactly the same capability, the ability now to generate and automatically handle client-side certificate management for you. So mutual TLS is a lot better, right? We're now in a situation where we've got the ability to validate who the client is and who the server is. We've got an industry standard, well-supported, with great automation tools available to those of us who are lucky enough to be on a cloud platform. So observation of data, yay. Manipulation of data, yay, yes, we've also fixed that. We've stopped accessing endpoints, and we've stopped impersonation of those endpoints. And even if I had to install this manually, when you're starting to send really sensitive information out to third parties, you still might install it yourself manually for things like downstream parties or sending information to our royalty streaming partner. But obviously, if you can automate it, just do it everywhere, right? Again, it's not adding much overhead to you. The problem, of course, is that the microservice architecture, lots of you are not using HTTP-based protocols. You might actually be using other kinds of protocols, maybe messaging protocols. So, if I'm using something like RPC, I might well be routing RPC over HTTP, which is, as is the case with something like Google's gRPC. But I'm obviously also communicating asynchronously via message brokers, right? Things like Rabbit and Kafka. And those aren't going over HTTP. They're using their own bespoke protocols. In those situations, you're going to need to look at what specific technologies and what approaches your own broker has in these situations. Now, both Rabbit and Kafka, which I think are fine choices, both have support for this. They both have support for equivalent technologies in the form of either sort of direct TLS and the ability to configure those things, and also the ability to also configure sort of access controls and ACL-based controls where you want certain teams and certain services to only be able to see certain topics. That stuff is very easy to do and has been out there for a long time. Likewise, Kafka, which is very popular for microservice teams right now, has support for TLS and Kerberos, and again, a very rich set of controls around access controls and limiting access to individuals as well on those topics. The key thing here is this isn't necessarily going to be generally applicable. The answer, if you're using different types of systems, if you're using NATs or end service bus or other types of asynchronous protocols, you're going to need to look into the detail of how they recommend that you secure and protect your systems. But have those 4 concerns at the back of your head when you're thinking about it. Now, what we've talked about so far is basically just transport authentication. It's basically we've confirmed server-side identity and client-side identity where both the client and server are computers, and we've confirmed whether or not they are who they say they are. And then we said, yes, you are who you say you are, and now you're authenticated. We know you are who you say you are. We haven't talked really about anything else other than that. We've only dealt with that part of the problem. The issue, of course, and what always complicates things, and as Jerry Weinberg once said, it's always a people problem, is human beings. Right? Because we actually have human beings in our system. And basically, as we've found for decades of computing, it's human beings that screw stuff up. So we've got the person in the street who's accessing our systems. Now, here we have our user interfaces. They're out there in the wild, our applications, our black mirrors sitting in our pockets. And normally what you would do in these situations is you'd have some kind of auth gateway. So when people are accessing the systems, that auth gateway will intercept any calls and go, oh, actually, you need to log in. And so we'll be looking at things like HTTP basic auth from the web. We're looking at things like OAuth, sometimes from the web, but obviously nearly always now for mobile, and some kind of OAuth or basic auth handshake And typically what we would do is have all of that handled inside some gateway that would sit in front of our services. So that once you get traffic behind that auth gateway, we know that only authenticated users have gained access to the rest of our system. So I hope that's all pretty straightforward stuff. There's some gotchas here, of course, because there's authentication of a human being, and then there's authorization of a human being. And that's why we often shorten it to auth, which means both authentication and authorization. And we often forget the authorization piece. The authorization is, what am I allowed to do? So authentication is, I am Sam. Authorization, and what can Sam do? This is where things get kind of interesting. So let's walk through a simple workflow. So here I am. I'm kind of trying to access the system, and I say, hi, I'm Bob. And the auth gateway goes, yeah, sure you are. Prove it. And so I'm made to fill in a little username and password, and I send that information off, and the auth gateway goes, OK, yes, you really are, Bob, and now you can access our systems with impunity. OK, great. So now Bob wants to go and access his profile. So he goes up and clicks on his account and says, OK, what are my details? And to do that, I'm going to navigate to this URL. I'm very old school. I like web pages. So we're going to a web page, which is like a single page app, only there's more of them. And so I go through, OK, can I have my details, please? And the web shop goes, well, I'm rendering this, but actually, I need information about you to put onto the profile page, and I don't store that information. That's actually stored in the downstream user service. So I'm going to go off to the user service and say, can I have Bob's details? And the user service is going to go, well, I trust you because of our, maybe we're using mutual TLS. I know you're definitely the music web shop. You're my buddy. I trust you. And so, of course, you can have the information. You're not someone nasty. So here's all the information you need. And here is now Bob's details get served back to the web shop. They get rendered into that HTML page. And lo and behold, Bob can see Bob's details, and the world is good. OK, let's run through a slightly different scenario, because Bob starts thinking nefarious thoughts, and he thinks, oh, look at that URL, as my name's in that. Let's change that. Let's put the word Alice in, because I know Alice is a user. And so he goes, can I see Alice's details? And the user web shop says, you're logged in, but I don't have Alice's details, so I need to go and send those and go and ask the user service for Alice's details. So he wanders off, and he goes to the user service and says, can I have Alice's details? And the user service says, well, you're the web shop. You wouldn't steer me wrong, would you? You'd definitely only send me proper traffic, and I trust you. So yes, of course, you can have Alice's information. And so I send back Alice's information, and the music web shop bundles it up, and lo and behold, I get Alice's information. And this is probably not what we expected, OK? This is an example of what's called the confused deputy problem, right, where you trick an intermediary party into asking for things they shouldn't ask for. It took me so long to find this clip art, by the way. Right. The issue is we haven't actually applied authorization in this flow. We haven't said, who are you and what should you be able to do? Now, the question then is, where would I stop this process? Now, one option is upstream. I could carry out that authorization process. I could say, hang on, you're Bob, but you're asking for Alice's information, and make that decision upstream, maybe in the auth gateway, maybe at the music web shop. The issue, though, is with the microservice architecture is we're breaking these things apart into independent services that have their own behavior and state and data. And it always feels a bit weird to me that the capabilities that I'm trying to authorize are all the way downstream, and yet I need to know about what those downstream capabilities are upstream in order to be able to authorize that. And that feels a bit backward to me. Ideally, it would be nice if the downstream services would be able to say, I know what the authorization scheme is because I have the information about what the authorization scheme should be because I also know what capabilities I expose. But typically, we push this upstream, and I think that's a bit backward and a bit wrong. A much nicer model is actually to have the user service be able to make a call about whether or not this information should be served up in the first place. The issue is the user service doesn't know who the user, the actual human being is that's asking. So it knows the music web shop is making the request, but what it needs to know is who is the music web shop making the request on the behalf of. So that you've got to say, not only are you're actually saying, you're asking for Alice's information on behalf of Bob, and I can then make a local determination about whether or not that is correct. So that's what we want, right? I want the user service to say, no, you can't have that information. But we need additional information. This is where people start talking about things like Jot tokens. So Jot tokens are basically JavaScript JSON web tokens. It's basically a mechanism by which you create a token with information about who a user is that can be proved to be true and correct, basically using hashing. And you pass that token along with the request as it goes downstream. That token can be validated and information extracted from it, and that allows us to safely send down information about our logged-in user. And so you get a token like this, which has the ID of the user and the name of that user, so Allison, and then you'd perform a hashing algorithm on that with a private key, and out would come a hash. This hash represents the token itself, and any service is able to validate if that token is true out of band just using, not out of band, sorry. It can just validate that token just by validating the hash, just using a standard public key. So this means no round tripping to check what this person is allowed to do. So I come along here and I say, OK, I'm logged in. And normally what happens in these processes is you'll be passing in an OAuth token or a cookie to represent your logged in state. And then what you do is you had the OAuth, so your authorization gateway is going to exchange that for a JWT token that we're going to then use within our perimeter. We don't want to leak that JWT token outside of our perimeter because we might want to put more information in it. So I generate that token, and that's in this situation might be as simple as saying the user is Bob. And when I make that call downstream, the token goes downstream. The user service is asked, can I have Alice's details? We first have that transport security that says, are you actually the music web shop? And once the answer is yes, I am, the next thing the user service does is it looks at the token, validates the token, makes sure it's not a faked token, and then it says, but you're Bob, and you're asking for Alice's information, and based on the logic that we have around authorization, that is not something that we allow. And so I'm going to say no, and we can pass that all the way back up. The nice thing about this is there's no need for a round trip in this process. The token can be validated locally without checking up again. You can also put more information, of course, into this token. You could say, actually, Bob's in the administrator group. And maybe the logic in the user service says, oh, if you're in the admin group, you are allowed to see information other than yours. The whole nice thing about this is we're trying to avoid round trips. A lot of the authorization schemes I've seen for microservice architectures that fix this problem rely lots of round tripping. So, OK, well, I've got this information. I've got to go and ask somebody else what I can do. One of the commercial API gateway vendors I spoke to who said they solved this problem, they basically put themselves on every single network call between every single service. So whenever you made a service call, you'd actually do a service call and it'd go out and then come back and then go to the next service. And it would go out and come back and go to the next service. And so you basically doubled the number of network calls you made across your entire system overnight. We called that latency as a service. So what we're trying to do here is balance these forces. We've got a token that can be validated in isolation, that can carry quite rich information, and that can allow the services to make the judgment call about what they should allow to happen in the first place. And so it's a really nice mechanism. And it's been quite widely used nowadays. And I think there's some support for validating Jot tokens as well in the Azure API management stuff as well, although I haven't used it myself. There's also new technology out there that's starting to make a lot of this easier. Some of you may have heard of service meshes. These are kind of new technology, things like Linkerd and Istio. And they basically work by almost working like a proxy in between every network call that you make. And that can insert new behavior into those network calls on your behalf, which means your application stack has to do less. If you think about service-to-service communication, it's a whole load of common concerns that we have. We have things like, how do I handle tracing? So I've got to have some code to ensure that I'm putting pulses out to my open tracing API. I've got things like load balancing and service discovery. I've got authorization and authentication, which we've been talking about so far. And I've also got things like connection, resiliency, and retry mechanisms. And because we keep repeating ourselves over and over again with this stuff, we end up creating common libraries and common frameworks so that our services do these things out of the box. Right? So on Java, for example, you've got things like Spring Boot, which when you use a Spring Boot framework, can bring all that stuff in for you. And there are obviously equivalents for the Microsoft stacks and other application stacks as well. The issue is that all these different frameworks all behave slightly differently, and a lot of those behaviors want to be consistent. The other issue with a microservice architecture is a lot of people want to use a mix of technology. So if I do develop or come up with the libraries for these common concerns around things like authentication and authorization, sure, I can use that and share that code where I've written these for Java, but I can't use that same code for my .NET application or my JavaScript application. I'm going to have to re-implement those for those different tech stacks or find equivalents. That's a lot more work. There's also the issue of things like version drift, right? I've got version 1 of my common authentication concerns in one service, but I've updated those as now we've changed our authentication scheme. And now some services have got the new authentication scheme. And now I've got this issue, well, can these things still communicate now that I've got incompatible potential versions out there? So the Sidecar model that came out of Netflix opened up some interesting possibilities that sort of created this whole service mesh idea. Netflix had this issue with JVM to JVM communication. They had a rich set of libraries to make sure that JVM to JVM communication worked really well. And the problem was that and they relied on that. And so for all machine-machine communication in Netflix has to go from JVM to JVM because of these really great libraries. But they said, well, we want to use other non-JVM-based languages. How do you handle that? What they did was they adopted a sidecar model. And so you run your service on the same machine as a sidecar. So that service could be written in Node.js or Python or PHP or whatever you want to. And it talks locally, so over a local network, so therefore not really a network and not at this point a distributed system, to my sidecar. And that sidecar has all that common libraries that handle authentication and authorization on my behalf. And that communication to other machines always goes via those sidecars. And so all those shared common concerns to handle things like authorization, authentication, maybe Jot tokens and all that sort of stuff is pushed out. Effectively, I'm getting code reuse without having to rely on libraries. This idea is really nice. So I'm reusing code across tech stacks. I'm reducing the impact of things like version drift. Service meshes take this idea to the next level. And they say, well, OK, now let's have this for everybody. So if you're running, say, on a platform like Kubernetes, you've got all your pods that are talking locally, and they're going to talk to, say, a local daemonized proxy. And all communication goes via those proxies. Those proxies then have the potential to do things like smart routing, so route to pods that are locally to you. And it sort of becomes a network effect, right? In many ways, this is implementing for our services what we get from message brokers with a nice control plane on top. Now, service meshes are really new. They don't work for all technology stacks. This is a new sort of era in these sorts of things. I think keep an eye on it, but maybe in a year from now, start looking at actually using these things because it's still a work in progress. We've covered quite a lot of stuff today. We've talked about patching and passwords, storing of secrets, transport security, so the authorization and things like the confused deputy problem, and we took a quick look at service meshes. Thank you so much for your time. The slides are already available up on my website, but I will be tweeting those out, as well as a link to a new 3-hour on security in the context of microservices. But thank you very much.